Titanium nitride is an extremely hard, inert, thin film coating that is applied primarily to precision metal parts. Titanium nitride, tin, is the most common PVD hard coating in use today. Tin has an ideal combination of hardness, toughness, adhesion and inertness. CSG titanium nitride, tin, coatings. General characteristics. Titanium nitride is the most frequently used ceramic coating on machine tools, and has the longest history. Bright gold in color, it is often applied where both wear resistance and appearance are important. Coating Services Group, LLC, deposits both single and multi-layer versions of this coating. CSG also offers unique surface finish and masking capabilities. Applied by an environmentally friendly PVD, physical vapor deposition, process, tin coatings do not affect substrate surface finish. Dime color range, dark gold, variable to light gold or even silver, SLP. Thickness range, 1 to 5 microns, 0.00004 to 0.0002 inches. Hardness, 2200 to 2400 HV, Vickers hardness. Maximum operating temperature, 600 degrees Celsius, 1100 degrees Fahrenheit. Lubricity, 0.5 coefficient of friction. Deposition temperature, 350 to 500 degrees Celsius. Thermal conductivity, low. Parts wear resistance, excellent. Biocompatibility, very good. Structure, single or multi-layer. Titanium nitride, tin, coating. Hard, harder than carbide, 3x hard chrome. Inert and stable material. Extremely strong adhesion, molecular bond to substrate metal. Broad range of substrates. Broad range of thicknesses. Thin film typically 3 micrometers, 0.000118 inches thick. Uniform coating with no buildup on edges. Follows surface texture of the part. High temperature tolerant. Electrically conductive and non-oxidizing. Non-toxic and FDA compliant for implant use. Resistant to most chemicals. Metallic gold appearance. Conductive, does not oxidize. Low fatigue, very high compressive stress. Environmentally friendly process. Use tin for. Eliminate scalding, fretting, micro-welding, seizing and adhesive wear. Smooth operation of moving components. Wear resistance on precision components. Holds sharp edges or corners. Cavitation erosion. Erosion resistance. Non-stick surface. Most materials will not adhere to tin. Low friction. Little dimensional impact, perfect for close tolerance parts. Enhances corrosion resistance but does not perfectly encapsulate the part. Productivity improvement. Make more parts per hour. Plastic molds fill faster at lower pressures and temperatures. Cutting tools run at faster speeds and feeds. Decreased downtime. Longer life, less frequent tool replacement and cleanup. Titanium nitride coatings general information. Thin film coating applied by environmentally safe, physical vapor deposition, PVD, vacuum system. Can be applied to most metals to provide enhanced surface characteristics, and can also be applied to some ceramics and plastics. Has the appearance of gold, but is an ultra-hard material. Is harder than carbide and chrome, off the Rockwell C scale. Is highly inert, will not corrode and has excellent chemical resistance. Can withstand elevated temperatures up to 600 degrees Celsius, 1100 degrees Fahrenheit, in air. Is non-toxic, used for medical surgical devices and food processing equipment. Is dense and non-porous. Is typically 3 micrometers or 0.0001 thick. has a uniform thickness that follows the contour of the part's surface. Forms an outstanding bond to the base material that will not blister, flake or chip. Tools typically last 3 to 10 times longer than uncoated tools. Titanium nitride, tin, sometimes known as tinite, is an extremely hard ceramic material, often used as a coating on titanium alloys, steel, carbide, and aluminium components to improve the substrate's surface properties. Applied as a thin coating, tin is used to harden and protect cutting and sliding surfaces, for decorative purposes, due to its gold appearance, and as a non-toxic exterior for medical implants. In most applications a coating of less than 5 micrometers, 0.00020 in, is applied. Tin has a Vickers hardness of 2400, a modulus of elasticity of 251 gigapascals, a thermal expansion coefficient of 9.35 times 10⁻⁶ K-1, and a superconducting transition temperature of 5.6 K. Tin will oxidize at 800 degrees Celsius in a normal atmosphere. It is chemically stable at room temperature and is attacked by hot concentrated acids. It is chemically stable at 20 degrees Celsius, according to laboratory tests, but can be slowly attacked by concentrated acid solutions with rising temperatures. Tin has infrared, IR, reflectivity properties, reflecting in a spectrum similar to elemental gold, O, which gives it a yellowish color. Depending on the substrate material and surface finish, tin will have a coefficient of friction ranging from 0.4 to 0.9 against another tin surface, non-lubricated. The typical tin formation is a crystal structure of NaCl type with a roughly 1:1 stoichiometry, TnX compounds with X ranging from 0.6 to 1.2 R. However, thermodynamically stable. A thin film of tin was chilled to near absolute zero, converting it into the first known superinsulator, with resistance suddenly increasing by a factor of 100,000. A well-known use for tin coating is for edge retention and corrosion resistance on machine tooling, such as drill bits and milling cutters, often improving their lifetime by a factor of 3 or more. Because of tin's metallic gold color, it is used to coat costume jewelry and automotive trim for decorative purposes. Tin is also widely used as a top layer coating, usually with nickel, Ni or chromium, Cr, plated substrates, on consumer plumbing fixtures and door hardware. As a coating it is used in aerospace and military applications and to protect the sliding surfaces of suspension forks of bicycles and motorcycles as well as the shock shafts of radio-controlled cars. Tin is non-toxic, meets FDA guidelines and has seen use in medical devices such as scalpel blades and orthopedic bone saw blades where sharpness and edge retention are important. Tin coatings have also been used in implanted prostheses, especially hip replacement implants, and other medical implants. Though less visible, thin films of tin are also used in microelectronics, where they serve as a conductive barrier between the active device and the metal contacts used to operate the circuit. The film blocks the diffusion of metal of the conductor into the silicon, but it is conductive enough, 30 to 70 μ middle.cm, to allow a good electrical connection. In this context, tin is classified as a barrier metal, even though it is clearly a ceramic from the perspective of chemistry or mechanical behavior. Recent chip design in the 45 nanometers technology and beyond also makes use of tin as a metal material for improved transistor performance. In combination with gate electrics, for example HF-SiO, that have a higher permittivity compared to standard SiO2, the gate length can be scaled down with low leakage, higher drive current and the same or better threshold voltage. Tin has also been used in fusion power experiments due to its ability to tightly bond with oxygen molecules. Due to their high biostability, tin layers may also be used as electrodes in bioelectronic applications like in intelligent implants or in vivo biosensors that have to withstand the severe corrosion caused by the body fluid. Tin electrodes have already been applied in the subretinal prosthesis project as well as in biomedical microelectromechanical systems, BioMEMS. The most common methods of tin thin film creation are physical vapor deposition, PVD, usually sputter deposition, cathodic arc deposition or electron beam heating, and chemical vapor deposition, CVD. In both methods, pure titanium is sublimed and reacted with nitrogen in a high-energy, vacuum environment. Tin film may also be produced on TE workpieces by reactive growth, for example, annealing, in a nitrogen atmosphere. PVD is preferred for steel parts because the deposition temperatures exceeds the austenitizing temperature of steel. Tin layers are also sputtered on a variety of higher melting point materials such as stainless steels, titanium and titanium alloys. Its high Young's modulus, values between 450 and 590 gigapascals have been reported in the literature. 14 means that thick coatings tend to flake away, making them much less durable than thin ones. Titanium nitride coatings can also be deposited by thermal spraying, whereas tin powders are produced by nitridation of titanium with nitrogen or ammonia at 1200 degrees Celsius.